Nobody really knows what entropy is, and if you use it in an argument, you will win every time. That's not what I'm saying, that's allegedly what John von Neumann said to Shannon. It's time to debunk this mystery. Entropy might seem elusive, but it's actually a quite intuitive idea, and a fundamental concept in information theory and physics. At its core, entropy measures the amount of disorder in a system. Have a look at these two messages. You might think that the left one is more informative, but guess what? The right one has the higher entropy, meaning it is more disordered. When reading the left message, predicting the next character comes easy, while the right one is unpredictable. Let's dive into physics. According to the second law of thermodynamics, the entropy of a closed system can only increase. This is also true for the entire universe. Its entropy is always increasing, meaning an ice cube melts when left alone. This is the same idea. Initially, it has a highly organized temperature. As air molecules collide with the ice cube's water molecules, they transfer energy, heating the water and cooling the air. This spreads out the well-organized energy distribution into an even and chaotic mess. Consequently, the temperature gradient weakens and the ice melts. But why does this happen? A probabilistic approach gives an answer. This highlights the connection between information theory and physics. Both fields involve this concept that, despite them appearing unrelated, share fundamental principles. When it comes to sending messages, only a small fraction of them exhibits a strong structure or low entropy. Creating a poem by randomly selecting characters, for example, is highly unlikely. It's much more likely that you create a chaotic jumble like our previous example. The same is true for physical systems. There are just much more configurations of the energy distributed evenly between the water and the air molecules than there are configurations where there's much more energy only in one place. Leaving the system by itself, it's much more likely that it ends up in a disordered or high entropy state. But if it's that easy, why did von Neumann assume it would confuse people? Behind this common sense argument, there's a deeper question. How does order emerge from chaos? How do molecules form intricate crystal structures? How do complex components like DNA arise? How do advanced life forms evolve if everything's ought to become more disordered? Energy plays a vital role in creating complex structures, but entropy still always aims to increase. Does the second law always apply, or are there some exceptions? How does this all come together? One thing to understand is that disorder and order is not the same thing as simple and complex. These are two different axes. So the question is what path the universe takes on its journey from low entropy to higher entropy. As the time flows from ordered to disordered, there are many states in between, and some contain very complex structures. When everything is neatly organized, we start at a simple structure. It seems unlikely that out of this simple structure's complex life could have emerged, but apparently it's the case. But time flows on and we end up at a complex but high entropy state again. The important point is that the meaning if a structure is simple or complex lies in the eyes of the observer, or more specifically, whether it is inside the intellectual boundaries. If we could do all the necessary computational work, then we could in principle see through the simple rules underneath. An unconstrained observer could arrange a simple system in a way that creates a specific structure by itself that looks complex to us. But because we don't understand the complexity of the initial state, it appears to us that the structure emerged from chaos. But wait a minute. Why does time flow only in one direction? All the laws of physics appear to be symmetrical. Therefore, they could also run backwards, except for entropy. Entropy only runs one way. Here's a vivid example. 2 billiard balls are colliding. It's impossible to tell if the video is played forward or backward. It's symmetrical. But add more balls and the emergence of order from chaos becomes increasingly unlikely. This is part of the reason why watching reversed video can be so fascinating. Because of this link of time and entropy, we could also think of time as a statistical phenomenon. It is not impossible that an ice cube is forming spontaneously from a puddle of water. It is just very, very unlikely. The same can be said for time. Time could run backwards. It is just very, very unlikely. Now, I hope you see entropy a little bit clearer and won't get tricked so easily if someone is using it in an argument. There's a lot more to say about entropy, and it has some interesting history as well. I'll leave some links in the description below you can check out if you're interested. Until then, I see you next time.